Hello, everyone. My name is Carolina Mattsson. I'm a postdoc at the Leiden Institute for Advanced Computer Science at Leiden University, and I am here in the Making Life Easier demo session number 2 to talk to you guys about Follow the Money, which is a Python program that I've developed to help make sense of financial transaction data. So the first thing I want to do is to ask if you've ever wondered, where does your money go? Like when you pick up a takeout meal, where does that money go? I am here to hopefully show you that this is not a hypothetical question. We pay one another using specific built infrastructure payment systems. It ends up being a patchwork. You've got digital financial services, credit unions, banks, national currencies, even Bitcoin, I suppose. And these payment systems, they host our financial accounts, they process our transactions, and they are increasingly digital. So I want you to imagine for a second the kinds of records that these systems store. There is a treasure trove of data out there about the real economy just sitting on the servers of financial institutions the world over. Now, there are lots of reasons why this data is not widely studied already. Payment systems are mostly private, there are major privacy concerns, human subjects considerations, etc. But a big part of it, I think, is that we haven't yet had the tools that we need to get started. Because if we do know what to do with this kind of data once we have it, I think we'll be better able to overcome these other barriers. So that's what this talk is about. I developed a Python program that lets us pull useful analysis records and interpretable results from payment system records. The general premise is not that complicated, so let me step through it real quick. What payment systems record are basically long lists of individual transactions, but these are far from independent. That's because payments move money. So let's focus on the fact that the payments actually happen. They move money from like A to B, like that. And that means that we can use these records to trace that money through the payment system. We end up with weighted trajectories of money or observed flows of money. And these can be useful, like a new perspective, a useful base for analysis. So I do that tracing thing for all of the money. The code that I've written systematically traces money from where it enters a payment system to where it leaves, from where it is deposited to where it is withdrawn. This is how you would use it. This is what it looks like. It's a Python code, so you would put Python in front of it. You have the program file that runs this transformation, takes an input file of ordered transactions, a configuration file with key system details, an output folder, and then you give it an allocation heuristic. More on that later. For now, let me talk quickly, mention what goes into this configuration file, kind of what do you need in order to get started here. So the first thing that the program needs is some basic information about how to read the file itself. So transaction header time format, as well as what is the observation window, so we know what transactions we see and do not see, to be able to kind of understand where we're starting and where we're ending. You also need to, if you have fees, transaction fees in the data, you need to record the convention. You need to tell the program the convention for recording the transaction fee, and then you need to provide a systematic boundary definition that the program can use to understand when money is entering and exiting this payment system. All right, I know you're thinking it, and I am so glad you asked. Why would we go through the trouble of transforming our transaction data into trajectory data in the first place? So let me give you an example of how we've used this to study mobile money. Mobile money is an up and coming digital payment system kind of thing. These systems run over cellular infrastructure in countries without a lot of banking infrastructure. You send money with the equivalent of a text message, be like USSD, and this digital system is supported by a network of in-person agents who act as human ATMs. You give them cash, and they boop e-money onto your phone. The specific data that I'm working with here for these results come out of collaborations between the IFC and Microfinance Opportunities on the one hand, and between Northeastern and Telenor Research on the other. So the first thing we can do with Follow the Money is to use simple descriptive statistics of trajectories to summarize e-money use. And we can do this because the sequential pattern or motif of transaction types corresponds to known use cases for mobile money. This here is the kind of stereotypical use case, which is a transfer. So it would be you cash in money from an agent, they boot money onto your phone, you send that to another person, and then they withdraw it again. So that is again a transfer. And we find that around 11% of activity over the system is used for transfers. Another common use case is to make a payment. So this would be a cash in followed by a bill payment or a top-up payment to purchase phone minutes. I call these the payment and micropayment motifs, and they also make up around 11% of activity over the system. I'll point out that the bill pay tend to happen really quickly. So it's another thing that trajectories gives us is kind of this aspect of time that we can look at. Naturally, of course, you can do each of these actions using money that's already in your account that like somebody else sent you versus cashing it in. This is the kind of thing that a provider would want to promote. Unfortunately for this provider, only around 2%, a little over 2% of activity comes from this circulating patterns. So the rest of activity over the system is constrained to follows the pattern of a cash in followed by a cash out. So this is non-digital activity, various forms of non-digital activity, and that makes up almost 72% of all of the activity on this system. So it's kind of an important thing for this provider in particular to keep in mind. To get these kinds of, to aggregate in this particular way, you would run now motifs.py, which is the program file for summarizing by sequential motif. You give it the main output file from Follow the Money, all of these trajectories. Again, you give it an output folder, and here you can also give it, you should also give it a maximum length for distinct motifs because they can kind of get infinitely long. So most of the ones I showed you are size 3, except the stereotypical transfer one, which was size 4. Next, another thing that we can do with trajectories is to model e-money savings and thus quantify the extent to which account holders use their accounts to save. To do this, I'm going to jump back and demystify this allocation heuristic that I mentioned. The reason for this is that money is fungible, and so to trace money through an account, we have to make a systematic choice about what money goes where in cases where that is ambiguous. Let me step through again an example. I think that's the best way to explain it. So this account here starts with $100 and then it receives another $100. Next, the account sends $50 to 2 different accounts. The last in, first out heuristic uses the most recent incoming transactions to fund the outgoing transactions, creating 2 $50 trajectories. The well mixing heuristic pulls evenly from both incoming transactions, creating 4 $25 trajectories. Now, let's look what happens if we vary the initial balance in B's account. Last in, first out is unaffected, while mixing is affected. That is because here now, the most recent transaction is now a much smaller fraction of the total balance, and thus a smaller share of outgoing transactions in the well-mixing case. Now, if we go the other way, you'll see that the two heuristics end up being equivalent because there's no ambiguity at all when the balance is 0. So here, what I'm doing is that I use last in, first out as a model for e-money savings. And we can do that because last in, first out mimics an intuitive idea about how people save money. In the sense that like building up savings means leaving money undisturbed for a considerable length of time in an account. So savings, you can kind of say that they under last in, first out, savings kind of accumulate at the bottom of an account until the account holder needs to dip into them. So yeah, this is the kind of the model of savings that last in, first out lets us study. And trajectories capture time. So with this intuition, we can quantify, the time that, trajectories capture time, this kind of holding time that money spends in accounts. So we can find the accounts that leave some fraction of their incoming funds undisturbed for longer than a week, 2 weeks, 30 days, whatever you want. Here are the results of this. I'm highlighting that point right there that I circle where we can say that 21.7% of users succeeded in saving over 5% of their incoming funds for over 30 days at some point during the observation period. You can also see that lots of users save teeny tiny amounts and very few users save large amounts. So again, this right here is the kind of the code that you would use to analyze the trajectories in this particular way within my code base. Users saving now is the program file for calculating these user saving rates. Again, the input to this analysis code is the main output from follow the money. And then you also go into the output folder. And then you'll give it a maximum length of time to consider. And then perhaps the most fun thing we can do is to use trajectories to map the flow of e-money through the system as a whole. To visualize this particular system, I group the motifs together and then aggregate by entry exit point. What that means is that I put together all of the trajectories with the same entry exit point, get rid of the users in between, and then we can look at the structure of mobile money. This is what payments look like. You get these really big hubs. With transfers, money ends up kind of moving all over the place. And then we actually find two different structures within the cash in, cash out subnetwork. The one on the left, we see are these tight little clusters of agents that we actually uncover that they are gaming the system. They're making lots of tiny little transactions through some user account that they control. And then one large transaction, they end up being paid more than the provider. So it's gaming the system. And then the rest of that network looks kind of more like what we would expect it to. So this is how the execution script that creates an entry exit network would look like. It creates lots of link variations that you can kind of slice and dice however you want. Again, program file, main output file, and then an output folder. This can be run in parallel if you first sort the trajectory by the entry exit points. So now to tie this together quickly, I have talked to you today about Follow the Money, which is a toolkit in Python for making sense of payment system records. You can summarize activity over payment systems, incorporate time dynamics such as savings, and also map the flow of money. This is where you would go to find it and use it. Last but not least, I want to acknowledge everyone that's been a part of supporting this kind of work. And I really hope that you will stick around to ask me questions.